All right, so in this little video, we will look at trends in charge on the periodic table. Now, here's the deal. I think there's a misconception about charge, in that when I see sodium +1 or chlorine -1, people think that, oh, the poor thing, it's got a charge. That somehow having a charge is a bad thing, or that it's not good. And it's totally the opposite. Having a charge is a good thing. Having a charge just means that the original neutral atom either gained electrons or lost electrons in order to fill the outer shell of orbitals. And when we fill the outer shell of orbitals, that's stable. And so the only elements that are stable when they're neutral are the noble gases, right? And the noble gases just naturally come with a full outer shell. So they don't really need to gain or lose electrons, and they really don't form ions. They're stable as they're neutral because they have full outer shells. And so whenever we talk about like achieving stability, stability means full outer shell of electrons. Everybody else is jealous of the noble gases. And so they want to have a charge. They want to gain electrons or lose electrons, whatever causes the least amount of commotion. But we want to try to achieve that full outer shell. And so because there are trends in valence electrons going down a group, you'll also see trends with charge. So for example, if I put like on the bottom, I'm going to write valence electrons. Valence electrons. So everybody in the first group, all of the alkali metals, have one valence electron. Their configurations will always end something S1. Okay, so with one valence electron, we're usually thinking, okay, we either lose 1 or gain 7, because if we're trying to fill the outer orbitals, not including the first energy level, we're usually thinking 2 electrons in the outermost s orbital, 6 electrons in the outermost p, for a total of 8. Well, if you only have one valence electron, it's easier just to lose 1. And if you lose 1 electron, your charge becomes +1. So everybody here has a configuration that's like something S1. 1 electron in the outer shell, they'll lose it. And again, the +1 charge, if I lost an electron, but I didn't change the number of protons, well, then there should be an extra proton in the nucleus compared to the number of electrons in the electron cloud. So +1, again, it does not mean that I gained an electron. It's a balance between protons and electrons. You've got 1 extra proton because you lost an electron. Everybody in the second group, all of the alkaline earth metals, they all have 2 valence electrons. Their configurations will all end something S2. So again, with 2 valence electrons, it's still easier to lose 2 rather than gain 6. So they'll all have a charge of +2. +2, 2 plus, same thing. I should also mention with like the alkali metals, plus or +1, same thing. If you just see a plus, it's understood that you mean +1. Maybe I'll write that in there. This means +1. Awesome. Then we're going to skip the transition metals. So these guys in the middle just don't follow trends real well. We're going to skip the transition metals. The transition metals. They're called transition metals because the number of valence electrons can change. It can transition, which means that it's hard to predict the charge. If we don't really know how many valence electrons there are, then I don't really know how many we're going to gain or lose to get an octet. Okay, then the trends will pick up again when you hit the p block. Now they didn't put it in here, so we can add it, that there are some trends in the boron family and the carbon family. The boron family and carbon family do get into other situations, but for the most part, everybody in the boron family is going to go +3 because their configurations will all be something S2, something P1. So the boron elements, boron, aluminum, gallium, their usual charge is +3. Especially like aluminum and gallium, +3. Carbon, the carbon family is kind of funky because they have 4 valence electrons. Here, I'll put this kind of in there too. So valence electrons, everybody in this boron family has 3. Everybody in the carbon family has 4 valence electrons. And so if you're going for 8, it's kind of a horse apiece, like gain 4, lose 4, yeah. They can go either way. And so sometimes we don't really see a charge written on top of the carbon family. If that bothers you, I usually just put plus or minus 4 by carbon. They can kind of go either way. And in the end, it's going to depend on what carbon is bonding with. Is it something that wants to gain the electrons, lose electrons? Then we can figure out if carbon's going to be the electron donor or the acceptor. But for the most part, it's safe if we say plus or minus 4 in the carbon family, because they have 4 valence electrons. But then for sure, when we get over to the nitrogen family, everybody's got 5 valence electrons. There's 2 in the outermost S and 3 in the outermost P for a total of 5. And now we kind of like turn the corner. So I have 5 valence electrons, I want 8. Well, rather than lose 5, it's easier just to gain 3. And now when I gain 3 electrons, if I have 3 extra negatives, my charge becomes -3. Everybody in the oxygen family has 6 valence electrons. Something S2, something P4. So they're going to gain 2. When they gain 2, their charge is -2 or 2 minus. And the halogens all have 7 valence electrons for a total charge then of -1. 7 electrons, just gain 1. And we're at 8, right? We're almost full. We're something P5, and we'd like to end that P orbital with 6. Cool, so here's what I might suggest. I might suggest go to your periodic table at the back of the book and write these charges in. I think it's really helpful because eventually we're going to be freaks about charge. And we're really going to want to know the charge on every element on the periodic table. Well, it's kind of nice to know that they follow trends. So all I would do is just go to the back of my book, the very last page that has the periodic table, and just on top of the first group, write +1. On top of the second group, write +2. Skip the transition metals. When you get over to the boron group, just write +3. When you hit the carbon family on top, write plus or minus 4. And that's the turning point. Now we go negative. So on top of the nitrogen family, just write a big -3. The oxygen family will say -2. The halogens will say -1. And the noble gases, you can put a 0. And the noble gases are not going to gain or lose electrons, most likely. And so they really don't have a charge. Fantastic. So now you'll always remember the trend in charge. Now obviously we might be asked to explain why does fluorine have a charge of -1? And then we'll talk about its electron structure. Oh, because we've got 7 valence electrons. Fluorine is 2s2, 2p5. And a stable configuration is when we have full outer orbitals, a full outer energy level. Which then kind of brings us to question 17, looking at patterns. When asked why a chlorine atom gains 1 electron to form an anion with a 1- or -1 charge, a classmate answered, because noble gas configurations are stable. Is this statement generally true? You bet it is. Yes. Yes, it is. Stable means full outer shell. outer energy level. Full outer shell, full outer energy level of electrons. And yeah, the noble gases just come naturally with all their orbitals full, with a nice full outer shell. So yes, the noble gases are stable, and then yes, a chlorine -1 ion would be stable. Chlorine would have 5 electrons in its outermost p orbital, the 3p. So it wants to gain 1 so that its electron structure will look like argon. There will be 18 electrons, even though the nucleus still only has 17 protons. But then that's why we have the -1 charge.